Alright, so I believe we are reaching the last video of chapter 5. Okay, so now that you have learned how to use the steam tables and how to do calculations from the steam tables, eventually you're going to use it on actual steam related problems lah. Okay, so if you remember our first law, okay, our SFEE, so the full form is actually like this: H1 plus half C1 square plus GZ1 plus Q equals to H2 plus half C2 square plus GZ2 plus W. So this is steady flow, which means this is a flow problem from the inlet to the outlet. The enthalpy at inlet, kinetic energy at inlet, potential energy at inlet, heat transfer in the system, enthalpy outlet, kinetic energy outlet, potential energy outlet, and work done in the system. Okay, so what we did was that we say that there are three types of devices. Okay, one type is your turbines and pumps. Okay, sometimes the assumption can be KE, the kinetic energy and potential energy, can be ignored. Okay, which means these two terms can be ignored, and it can also be in its simplest form, there is no heat transfer, which means the system is insulated. So Q, right, or rather Q is 0. In this case, your SFEE can be reduced to H1 is equals to H2 plus work done. Okay, and if this is a turbine system, your H1 will be higher than your H2. Then your work done will become a positive work because the turbines generate energy. And this is a pump. Your work done will be on the water, means your H1 initially will be lower than the outlet. So you will get a negative work, meaning that the electrical power, right, is providing energy to the fluid itself. Okay, so the second class of devices are boilers. Okay, boiler and or condenser. So the usual thing, KE and PE can assume to be negligible. And what you get, and because the whole system has no moving parts, you can assume that no moving parts means the work done is 0. Then your equation becomes like this. Okay, and if it is a boiler, the heat will be transferred into the liquid itself. So the initial H1 should be lower than the outlet H2. Okay, if it is a condenser, means the fluid loses heat. So your H1 should be higher than H2, meaning that Q will be a negative heat loss. Okay, meaning heat loss. And lastly, we have nozzles and diffusers. This one you can assume that the PE is negligible. Okay, a lot of times you can also say that there is no heat transfer, and because these are just fixed geometrical objects, your work done is also 0. So, but we cannot ignore the kinetic energy change because that is the key. So your equation SFEE eventually becomes like this. Alright, with the kinetic and enthalpy remaining. So in fact, these equations apply not just on perfect gas, it also applies on steam problems as well. Okay, so if the problem gives you a turbine, then you should know roughly which terms to use, which values to find. Okay, so let's just use an example, which happens to be the last example, 5-6. Okay, you have a boiler here. Okay, and then the mass is 50 kilogram and it starts at 30 degrees Celsius. Yes, I realized that I have not gone through one more thing. Never mind, let's continue. 30 degrees Celsius into superheated. And this is water. Note that this is water. Okay. I'm just going to prepare my question. Okay. And it goes to superheated at 30 bar. Superheated steam, 30 bar and 300 degrees Celsius. The superheated steam enter a turbine and is allowed to expand adiabatically, meaning there is actually two processes. From point 1 to point 2, okay, boiler, and from point 3 to point 4. Actually, point 2 and point 3 are the same. The outlet of the boiler is the inlet of the turbine. So this one gains heat, this one does work. Okay, the steam does the work. So this at the 30 bar, 300 degrees, it will go into the turbine and produce work and come out at a lower sort of energy state. Okay, so this is what is happening. So let's try to solve this question. So A, determine at the enthalpy of the steam at the boiler outlet. Okay, meaning state 2. Okay, enthalpy, since you have 30 bar and it is at 300 degrees Celsius. Straight away you go to the steam tables. 30 bar, 300. Okay, you should identify that it is a superheated. Okay, and the enthalpy is 2995. Yeah. H2 is 2995 kilojoule per kilogram. Okay. Amount of heat added to the water in the boiler. Meaning that boiler, we use the boiler equation. Okay. H1 equals to Q plus H2. So part B, right, is H1 equals to H2. H1 plus Q, sorry. H1 plus Q is equals to H2. Okay, H2 you already know is 2995. Okay, but H1 you do not know. And the idea is H1 is at 30 degrees and actually it is water. Okay, so now the key thing is this. If you are talking about a state under the hill, okay, and you use dryness fraction equation. When you use dryness fraction equation, you're actually trying to balance, trying to find the actual value between the F line and the G line. Okay, so you're doing some sort of an interpolation. Okay, and if you are in the superheated region, okay, so let's say if you're in the superheated region, and you're trying to do some interpolation, you're trying to get one figure here, you're also using two values to interpolate for a value in between, right? But what if you're at the left side of the hill, which is the subcool liquid? There is actually no value here. You only have, the only value that you can use to approximate is the F line. Okay, so let me show you again. So if I'm looking at this, 30 degrees Celsius, let's say it's this line, 30 degrees Celsius. Okay, but you know that it is a subcool. Okay, and for example, I can just draw this one bar, right? It doesn't, okay, does not really matter what pressure is this point at. Because why? Because what you are trying to approximate, H1 at 30 degrees, right, is approximately the HF at 30 degrees Celsius. Okay, which means for this case, you can go to page 2, 30 degrees Celsius, HF will be 125.7 kilojoule per kilogram. Okay, so this is the approximation to state 1. Okay, 30 degrees water. You use the HF at the given temperature. Okay, even if, let's say, I'm given 30 degrees Celsius and it is at 1 bar. which is exactly this point, 30 degrees Celsius at 1 bar. I actually have two values of HF to consider. I have the HF at 1 bar. I can either approximate this H to this point, HF at 1 bar, or I can approximate to HF at 30 degrees Celsius. Okay, so now what we're trying to say is that the actual value will be closer to this value. Okay, so use the HF at that temperature to approximate. Okay, so in this case, we are using the HF at 30, you get 125.7. Alright, and so now you have H1, and all you need to find is Q. 125.7 plus Q equals to 2995. Alright. So the Q is 2869.3 kilojoule per kilogram. Okay. But what the question is asking is in terms of kilojoule, not kilojoule per kilogram. So you're actually trying to find the whole system Q, which is basically the mass times specific heat generated. Okay, so this is 50 kilogram. Then you just multiply by the small q. You will be able to get 143,465 kilojoule. Alright, so this is the answer for part B. Part C. Degree of superheat at the turbine inlet. Okay, like I said, turbine inlet state 3 is actually the same as the boiler outlet. So your temperature is 300, your pressure is 30. Okay, degree of superheat is that temperature minus the boiling point at that pressure. So your case is at 30 bar. So it is 300 minus, what is the boiling point at 30 bar? It is 233.8. Okay, 233.8. And your answer, you get 66.2 degrees Celsius. Okay, so now, specific work done by the turbine. So now we are looking at the other process already. Okay, so now instead of looking at the boiler, we now look at the turbine. So from point 3 inlet to point 4 outlet. Alright, so your equation will then be different. Your equation will be the one turbine, H1 equals to H2 plus W. Okay, H1 equals to H2 plus W, and H1 is the inlet of the turbine, which is the same as the outlet of the boiler. Okay, which we gather just now is actually 2995. Alright, H2 is the outlet of the turbine, is P equals to 0.4 bar. And the dryness fraction is 0.85. So if dryness fraction is given to you, for sure this state 2 is under the hill, it is wet steam. Okay, so how you find is just use the dryness fraction equation. H equals to HF plus 0.85 HFG. Okay, so we're just going to go for 0.4 bar. Okay, here. So the H is here. 318 plus 0.85 times 2318. Okay, this will give you 2288.3. Okay, so you just put this as H2 here, 2288.3 plus W. So straight away you can see the W is a positive number because the turbine the fluid is doing the work. Okay, so this will give you 706.7 kilojoule per kilogram. This is specific work done per kilogram. Okay, but what about part E? Part E finally, the turbine output, power output, if the mass flow rate is 5 kilogram per second. Okay, in order to find power, this is, the unit is watts, right? Watts is actually joules per second, right? If you break it down, it's joules per kilogram times kilogram per second. Okay, so it can be a form of specific work multiplied by mass flow rate. Okay, so power is specific work times mass flow rate. So your case, your specific work is 706.7 kilojoule per kilogram, and your mass flow rate is this, 5 kilogram per second. So if you look at the units, the kilograms cancel out. Your answer will be 3533.5 kilojoules per second. So kilojoules per second is kilowatts. Okay, but the question asks in terms of megawatts, right? So megawatt is just 1000 kilowatt lah. So move 3 decimal places to the left, you get 3.533 or 34 megawatt. Okay, so this is how you find power. You need to get the mass flow rate. Sometimes the mass flow rate is not so direct. Instead, you will be given a diameter with a flow speed, if you still remember this, and then you will have your volume flow rate. If you can still remember chapter 1, cross-sectional area times velocity. So your velocity times pi d square over 4. Okay, this is just volume flow rate. You still need to multiply by density. Okay, so the density is actually very simple. Then because your steam, the volume that you find, right? The volume, the specific volume in the steam table is just 1 over density. So density is 1 over specific volume. Okay, you get the value of specific volume from the steam tables, you just invert it, you can get your density, and then multiply by cross-sectional area and the speed, the velocity coming out from the pipe. So that will give you your mass flow rate, okay, which you will multiply with the specific work. Okay, so that's it.